Okay, welcome to the first lecture for the first online video of Acoustical Oceanography, a course offered at Dalhousie University. And we're going to start with the absolute basic question that you have to ask yourself when you want to study acoustics. That's the question, what is sound? And particularly we're going to look at what is sound in a liquid. So, starting off here, lecture 1, what is sound in a liquid? That's the question. That's all we're going to answer today. And I think we can all answer that phenomenologically, like with our own experience, our own physical intuition, right? So basically, most of us would say, okay, what is sound in a liquid? Normally I'd ask you this, but you're watching this like weeks later, years later, who knows when. Okay, sorry. I'm going to try not to editorialize too much, but I want to make it somewhat fun. So what's the intuitive answer? Well, we'd say variation in, now this is where people tend to diverge. So you might say, all right, we're going to say variation in pressure as a function of position, right? And some people might say, well, actually, as a function of time, okay? And then other people, well, they say not pressure, it's actually variation of density. Well, okay. And other people might say, oh, actually it's particle velocity, right? The particles are moving in certain directions. They have different velocity change as a function of time and space. And the true intellectuals will say, I don't know, it's actually entropy. But, that's only for your thermodynamic heads out there. So this is our phenomenological, intuitive description of sound. But I want to go through with this first lecture and answer this question a little bit more mathematically. And the reason to do so is not to, make learning of the derivation of the acoustic wave equation an important aspect of the course, but actually the assumptions that go into deriving the acoustic wave equation, I think, do give some insight into why it has certain properties. Okay, so where do we start when we're deriving anything in physics? Well, okay, yeah, pretty much anything. I'm going to say that. I'm going to stick by my guns here. Where do we start when we derive anything? Conservation laws, right? So what does conservation of mass look like in a fluid? Conservation of mass. Got to underline that, so important. What do? We have to first draw an arbitrary volume, and we're going to call this V, and it's bounded by some surface S, and has a little patch and some normal vector that surrounds the whole thing. And the first question is, okay, well, conservation of mass. Well, we have a fixed volume, right? And we'll make our lives easy. We'll say that we're in the reference frame of the volume, so it's essentially it's non-moving. According to us, it's non-moving. Okay, that's going to make life a little bit easier. Non-moving V. Okay, so how do we write its mass? Well, yeah, okay, most of us will say capital M, and then we're going to integrate over the entire volume and integrate the density, right? Which can vary as a function of space, it can vary as a function of time, times dV. So very nice definition of the mass. Now, what is it when we apply some conservation rules? So by mass conservation, what do we want to equate it to? Well, usually what we say is okay, no mass is created inside this volume or destroyed inside this volume. So a change of the mass as a function of time is equal to the flux out. So how do we write the flux out? Well, we're going to write a surface integral, and I'll use a minus sign to indicate out, over the surface S, right? Density times the velocity dotted with that normal vector we so conveniently defined, right? So that's a nice mathematical definition of flow of mass out of the volume. And I'll just write here flux out, and this of course is change of mass in time. So what is this equal to? Well, we can rewrite our dm dt. We can actually just sub in the definition we wrote there into the differential, and then we're going to have d by dt of the volume integral of density over the entire volume. So this isn't so convenient because we have a surface integral here and a volume integral here. So we can't really do much with that. But what do we know that can help us solve this conundrum? Classic tool, I'm sure you learned a long time ago, Gauss's theorem, okay? Probably saw it in the context of electricity and magnetism, but of course we're dealing with wave physics here, so there's going to be lots of shared stuff. So, yeah. Okay, let's go to another page. So, okay. So Gauss's theorem. Let's remind ourselves about what Gauss's theorem is. We have the integral of over a surface of some field dotted with the normal outside that surface. That's representing the flow out. And then we have the volume integral over the divergence of that field. These things are equal. And of course, let's just be totally complete, define our del as the spatial derivative in all three directions. So from that simple conservation of mass, so our conservation of mass becomes, we move everything over to one side, and now we have the time derivative of the density, del dot the density times the velocity, integrated over the entire little volume, that equals 0. Okay? And we've done, of course, nice little Feynman's favorite trick, differentiation. Under the integral, classic trick. Okay. And our so because the integrand, this whole thing's equal to 0 to within a constant, we're going to say that the integrand has to be 0 because the integral is 0. So we're going to have this new conservation of mass is just the integrand equals 0. Okay. Very useful equation. Look, we can even do something like, oh, no. Trying to use the tools here. Trying to use the tools. Look, oh, look, this is important. Wow, okay. Yeah, it's not as much fun as writing on the board, but we'll go with it. Okay, so now let's consider a fluid particle. Oops. Yeah, okay. So we say the mass is constant. And we want to write down basically the most useful thing, which is, of course, F equals ma. And, you know, if we're a little bit more sophisticated, we'll say mass times acceleration is equal to the change in momentum, right? I believe that's, you know, a little bit more accurate, or a little bit more accurate to the historical definition of Newton's equations, Newton's second law. And then we're going to say more comfortably that's equal to the sum of the forces over the body. So how do we write all those out? Let's first write the momentum. So we have the delta is going to become a d by dt. And the momentum part, well, we know that's just mv. We already know what m is, right? It's the integral of the mass over the entire volume. So we'll say that times the velocity. That's going to be our momentum piece here, right? And then we want to equal that to all the forces. So what do we have in terms of forces on our arbitrary volume? Well, we have arbitrary forces, right? So let's say we have the integral over the surface of surface forces, and then we'll have body forces, right? Integral over the volume of body forces. So, for example, gravity is very small here. So, oops, body forces, and I'm going to say gravity, gravity, very small. So let's just say these are 0. Love writing something down and crossing it out. It's nothing, no better feeling in the world. And then, of course, here we're talking about surface forces. And what do we mean by that? Well, this could be, say, molecular agitation, right? So you have molecules bumping up against the surface, and coming with that, you know, a bigger, more bulk way of thinking of that is momentum transfer. You can have momentum flowing in or out of the body. And we're going to assume that these forces are normal to the surface, okay? Assume, so surface forces, their direction is going to be against that vector p that we defined, or n, sorry, that we defined at the beginning, and we're going to call these forces pressure, okay? So almost a spoiler, but so it's a bulk property of the fluid, okay? So next page. So we need the sum. We need the sum of Fs over the surface to be finite, right? So as to not tear the surface apart. And as the volume tends to 0, the pressure doesn't depend on the orientation of S. So, you know, as we shrink that volume smaller and smaller, we need that sum of Fs to be finite over the surface, so that we don't tear things apart and have some discontinuity, right? And further, P is independent of position. If that's true, so why not put an if, further if, then the net Fs must go to 0, right? Integrated over the entire surface. So let's go back to our equation and let's apply Gauss's theorem. So by Gauss's theorem, wow, we've already used it twice in one lecture, so it must be important to know. If you have a surface integral of Fs over ds, we have that equal to a volume integral of the gradient of P over dV, right? And you see that works because we have Fs is equal to minus P, and by our definition of pressure. So what is the gradient of P then? It's an equivalent force per unit volume due to pressure. That's what the gradient of P is, and of course we have some hint of what what P is itself. We talked about it's the surface force per unit area, right? So now we want to go back to our equation and bring the d by dt, right? We had a d by dt that we had to bring under the integral. So now bring d by dt inside the integral on left-hand side. So what do we get then? Well, our integrand becomes this messy thing, right? We're going to have rho times d by dt of v, right? And v is a function of x, which is a function of t, y, and z. Okay. And I'm going to put a little subscript p here and make sure I have enough brackets. And I'm going to say x of p of t is the position of the fluid subparticle. Within the volume V. Okay. So what do we need to do when we see some sort of nasty thing like this? We just need to do chain rule, right? So by chain rule, we're going to have rho d by dt of v x of t is going to be first dv dt, and then dv dx dx dt plus dv dy dy dt. Now, I know what you're thinking. You're like, why are you even writing this all out? Because it's going to simplify real fast. And of course it does. dv dt plus v dot del times v. And we define that, if you've taken fluid mechanics course before, as the total derivative. Okay? And really what this is, it's the time rate of change of within the moving frame of the fluid. Okay? So I think it has some other names, the vective derivative, but time rate of change within the moving frame of the fluid. Okay, so let's rewind a whole bunch and go back to what our equation can look like now. So on the left-hand side, we had d by dt of the volume integral of the momentum. Hopefully you remember that. And then we have, that becomes the volume integral of this total derivative times the density, okay? And so what have we done, just to recap, we've neglected body forces. So the whole thing, right? So if we cross off that body force on the right-hand side, if you remember back, the whole thing is now plus del P equals 0. And we'll make the same argument. We'll say, well, if the integral is 0, the integrand is 0. And so we'll write the integrand as an equation, right? And so really what we have here is we have density is mass over volume, right? We have that times this acceleration term. We can think of it that way. And then we have force per unit volume, right? We said that was one way to interpret the gradient of the pressure. And this is caused by spatial variation of P. So the changes in the pressure as a function of space are what give that force per unit volume. Okay, next page. Okay. So how do we get into really starting to talk about small fluctuations and really, the acoustics part of that? We've really just been talking about the dynamics of a fluid so far. So the acoustic disturbance. Okay. So what we're talking about here, very small amplitudes, right? And basically perturbations. If we're talking about pressure, right? Perturbations about an ambient state. And really you can think of that, I say pressure because that's very, something we measure a lot, but you think about it in density as well, think about it in velocity, right? So what we're going to do is we're going to linearize. Don't worry, my handwriting's this bad on the board as well, so this is not something special here. Linearize ambient state. Sorry, I should say linearize about ambient state, which we'll call rho naught, P naught, V naught, okay? So this is an old trick. I'm sure you've seen it maybe discussing turbulence before in the past. Pressure is equal to P naught plus P prime. Density is equal to density naught plus density prime, okay? And we're going to say we have a homogeneous medium. Which in other words means that it's this everywhere, which is mostly true, but won't, these are the types of things you need to, keep in mind. And this little bit here, this dotted bit, is really going to be our acoustic signal. This perturbation about the mean. We're also going to assume that we have a quiescent state of the fluid, which in other words means that V naught is 0. So we have this non-moving fluid. Just makes our life easier. So what is our mass conservation? Going back to our first equation, what does it become? Mass conservation. Let's recall. I love writing a recall. Recall, mass conservation. So d by dt, rho naught plus rho prime, right? This was the mass conservation that we defined, we derived. Then we have del dot rho naught plus rho prime times V prime, because we've said V naught is equal to 0. And that whole thing is equal to 0. And that equation we just derived last page, let's do the same thing, right? Which, some of you may have recognized, and I don't think I said the name, but Euler's equation becomes rho naught plus rho prime d by dt plus v prime dot del times v prime equals the gradient of p naught plus p prime. Okay, so we're going to multiply all this out and only keep the single primed terms, so the first order terms. So take first order terms only. And so you can see that some interesting things would happen if you kept the higher order terms. And this is sort of where we are turning away from nonlinear phenomena and sticking with linear phenomena. So a very important little divergence in the trail. So what does a mass conservation of mass equation becomes? Simply d rho prime dt plus rho naught del dot v prime equals 0. And the Euler equation or momentum equation becomes del naught dv prime dt equals minus the gradient of p prime. Now, very useful, but we also must relate p naught and rho naught, right? We need some relationship between p naught and rho naught. And so actually we need to go back to, an equation of state, right? We must also relate P and rho. So density and pressure, we know have some relationship, just from thermodynamics, but we don't know what that relationship looks like. So we'll define, define an equation of state. And this is a whole different field of study, thermodynamics. Whoops, wow, my writing's getting worse. We were only like 20 minutes into the first lecture. So right, think of things like PV equals nRT, right? There's a relationship between density, pressure, temperature, right? Of course, there's one for our fluid as well. And so we're just going to be very general. We're going to say P equals P with some function of rho. And if we sub in our linearized perturbation, we get P naught plus P prime is equal to some function P naught, rho naught plus rho prime, right? And then we'll do our favorite thing ever in the history of all derivations, and we'll take a Taylor series, right? So we'll linearize that. We'll linearize this unknown relationship P on the right-hand side, and then we'll have P prime equals dP d rho all naught times rho prime plus ... terms that are too hot to handle, or in other words, higher order terms. And so that allows us to derive P prime equals C squared rho prime. Whoa, what's C squared? Just brought that out of nowhere. Of course, we know that's the hypotenuse of a triangle. Just joking, it's the sound speed. So this gives us a definition of, from the equation of state, we can derive a sound speed without knowing anything about the form of that equation. And so we can say now C squared, of course, by the equation above here, is going to be equal to dP d rho, right? I think that's a pretty intuitive way of understanding, where the sound speed comes from. So we're pretty close, right? We have, so what have we done so far? We have the linearized acoustic approximation. Oops. Okay, yeah, I'm learning how to use this tool. And we can combine it with our linearized equation of state. EOS, just some lingo there. So what we're going to do is we're going to sub in the equation of state to our mass conservation equation. And we're going to wind up with a d by dt 1 over c squared dp prime dt plus rho naught del dot v prime equals 0, right? The whole thing. Let's bring that time derivative into the equation. So I have 1 over c squared, the second order time derivative of p prime, plus rho naught d by dt of del dot v prime, right? Starting to look pretty familiar here, but what's this term here? We're going to use our momentum equation now. Say del dot rho dv dt. Use momentum equation. And that's going to bring it, we're going to have a del dot minus the gradient of p prime. Okay. And so what does this all become then? Right? This. Oh, okay. Well, we're going to have replacement of pressure minus 1 over c squared dp dt squared. What have I forgotten? I've forgotten the primes, right? Should I put the primes in there? I'll leave the primes out because really we know that we're talking about acoustics here, and we know that we're talking about the perturbations in pressure. We're not talking about the hydrostatic pressure, for instance. And there you have it. I got to do this. Let's see here. Oh, no, don't want that. No, I'm really bad at this. Okay. Okay, well, I'll just do what I would do in the chalkboard. Put that in a big square, because that's your acoustic wave equation, right? That has that variation in space in the first term, the variation in time. We've got the sound speed in there. And so, oh, there we go. Like this would be so much better. Like, yeah, sure. We've got the variation, right, in space. It's variation of time here. We've got our sound speed, which we've defined very simply for now from our equation of state. And that gives us everything. That's all of acoustics, everything we need to know, all done in the first lecture. And a little bit faster than it would be in class because no one interrupted me, which honestly I miss, but no problem. So that's it for the first lecture. Thanks for watching. I guess I should probably say hit like, subscribe, comment. I don't know.